Okay, we're going to talk about graphing some polar equations. Now, when we were converting equations, I was kind of trying to point out, hey, this is the function in rectangular form, so it's going to look the same in polar form. The equation's just going to be different. Well, what we're going to look at now, we're going to look at some polar graphs that we can't create in the rectangular system. I'm going to create some graphs that are kind of exclusive, I guess you'd say, to the polar system. Except for this first one. This first one can be graphed in either system. Based on what we've learned the last couple of days, can anybody tell me what that would be the equation of? I think I heard somebody say a circle. That would create a circle. Okay, so let's see how. All right, let's see how. So instead of x being our independent variable, theta is now our independent variable. Theta is what we are plugging in to our equation. Then we're going to see what we get out. So we can definitely use our calculators. I have the table labeled in degrees. I could just as easily have it labeled in radians. So since it's in degrees, we do need to put our calculator in degree mode. Because, yes, I am going to use values that are from the unit circle. So it'd be great for us to review what those values are, but we're graphing. So the square root of 3/2 doesn't really do us a whole lot of good if we're trying to plot that point on the graph. We really do need that decimal value. So let's plug in all these thetas and see what we get for r. So for cosine of 0 gives us 4. Why? Because the cosine of 0 is 1. So we get 4 there. For cosine of 30 gives us 3.46. For cosine of 45 gives us 2.83. 60 gives us 2. 90 would give us, can anybody tell me before I type it in? 0, because the cosine of 90 is 0. And we're going to keep going. Okay, 120 gives us -2. 135 gives us -2.83. We're getting some repeating going on, are we? 150 gives us -3.46. What's 180 going to give us? -4. 210. I think I extended the table a little bit beyond what y'all had originally before I copied it. So just add these to the bottom. 210 gives us -3.46. 225 is going to give us -2.83. 240 is going to give us -2. And 270 it's going to give us 0. All right, so we have a table of values. We're trying to graph something, so we can always just take our table of values and plot those points, correct? So when theta is 0, 0 is right here. R is 4, so we've got a point on the line for 0 at the 4th radius. Okay. Notice how my graph here is broken up just like the unit circle is. So then that next ray there represents 30 degrees. So then 3.46 for the radius means we're about halfway between the 3rd and the 4th radii. 45 degrees would be our next ray. So it's 2.83, so more than 2, closer to 3. 60 degrees is our next ray. It has a radius of 2. 90 is obviously right here, but we have a radius of 0. So that just gives us a point there at the origin. All right, 120, we're going in order. Okay, 120 would be our next ray, but it has a radius of -2. So what does a negative radius do? Shoot you through the origin. So we're actually down here on, what would that be, 300? Okay, 135 is -2.83. Same thing. 135's out here, but it's a negative radius, so we go straight through the origin to the other side. So that's actually on the angle 315. Then we got 150. That also has a negative radius, so we go through to -3.46. Got some lovely symmetry going on here. 180. It has a radius of -4. Well, we already have that point. We already had that one. So sometimes with polar, points end up getting repeated. So like with 210, we've got a negative radius, so we go through to -3.4 to 3.46 on the other side. We already have that point graphed. That's going to happen with 225 and 240. The same thing's going to happen. And then 270 has a radius of 0. So let's, well, I think we already recognize that the equation is a circle, and you can kind of see how these points are somewhat circular. I didn't do a very good job of graphing super accurately, but they do form a circle, so connect them in a circular fashion. Let me point out that if you put your calculator in polar mode, okay, it will graph it for you, but you have to be in radian in polar mode, just FYI, radian and polar. And then you can go to your y equals, and it's now r equals, so 4 cosine of theta. And you can hit graph, and it'll graph it. It doesn't look very circular, but that's because our window is wider than it is tall. So if you zoom square, number 5, it'll make it look more circular. Okay, so you can see that circle. If you go to the table, you can see some of these values. Some of you are familiar with adjusting your table. You can, let's see here, table set, second window. We want it to start at 0, but the delta table, we don't want it to count by ones. If we're in radians, we want it to count by like pi over 12. And it will give us those values. Okay, it'll give us those values. You may be able, you know what? I may be wrong. You may be able to leave it in degree mode. Let me change this to 15 degrees. Let's see what happens. Yeah, that'll still work, I think. It doesn't want to graph it. Okay, so the table will look nice and pretty with the degrees that we need, but it won't graph it. You do have to, I was right, you do have to be in radian mode in order for that to graph. Okay? All right, so if you flip your paper over, you will see this summary. The graphs of r equals a cosine of theta and r equals a sine of theta are circles that have a diameter of length a. So the one that we just did had that 4 in front of the cosine, so it had a diameter of 4. Now these circles specifically are centered. If it's cosine, it's going to be centered on the x-axis. Cosine goes with x, makes sense. If it's sine, it's going to be centered on the y-axis. Sine goes with y, okay? We did look at some equations where we ended up with both variables, where we ended up with sine and cosine. That's when it's going to move it off of an axis, okay? But these are kind of the special graphs you need to be familiar with, okay? So cosine goes with x, so it's centered on the x-axis. Sine goes with y, it's centered on the y-axis. And the diameter is length A. All right, let's look at another type of polar equation. This time we have 1 minus the cosine of theta. So for the sake of time, to fill in this table, instead of having to type all that stuff in, I'm going to type this equation into my y equals, or in this case, r equals 1 minus the cosine of theta. I'm going to put it in degree mode, and I'm going to set my table so that it counts by 15 degrees. And I'm just going to go to the table to get these values. It's just going to save me some time instead of having to type all that stuff in. So 0 is still, well, in this case, 0 is 0 because the cosine of 0 is 0. 30 degrees is 0.13. 45 degrees is 0.29. 60 degrees is 0.5. Is this coming out right? Yeah. Okay. 90 degrees is 1. 120 is 1.5. 135 is 1.71. 150 is 1.87. 180 is 2. And I added a few more values to my table again. 210 is 1.87. 225 is 1.71. Yes. 240 is 1.5. And 270 is 1. So let's plot them. 0, 0 at the origin. Okay. 30 degrees is 0.13, so we barely really move out of away from the origin there. 45 degrees is 0.29. Again, we've moved out just a little bit. 60 degrees is 0.5. 90 degrees is 1. 120 is 1.5. 1.7. 1.9. 180 is 2. 210 is 1.87. It's like we're spiraling back in. 270 is -1. I didn't go past 270 on the table, but in my calculator here, I can keep going. Look what happens. I start spiraling in again. I've got for 300, 0.5. For 330, 0.13. For 360, we're back at 0. So what this has created is kind of like a flattened out heart. Okay, it has that dip there on the right side. It just doesn't have the point on the left side. If I switch this back to radian mode, I can graph it. I can see it on here. Probably want to zoom in a little bit. That doesn't show me very much. Okay, I can see it with a little bit greater detail there. Okay, these are what we call, oh wait, I have another one. My bad. 1 plus 2 sine of theta. Okay, 1 plus 2 sine of theta. Let's look at that one. Okay, I'm going to do the same thing. I'm going to put in my y equals, put it in degree mode, go to the table, copy these values. This time at 0, we're at 1. 30 is 2. 45 is 2.41. 60 is 2.73. 90 is 3. Phone should not be out right now. 120 is 2.73. 135 is 2.41. 150 is 2. 180 is 1. 210 is 0. Kept going on this one. 225, -0.41. 240, 0.73, 270, -1, 300, -0.73, 315, -0.41, 330 is 0, 360 is 1. So 0, 1, 30 is at 2, 45 is at almost 2.5, 60 is at 2 3/4 almost, 90 is at 3, 120 is coming back in, 150 is at 2, 180 is at 1, 210 is at 0, okay, 225 is right here, but it has a negative radius. So we go through. So we end up with 2 points up there on our 45-degree ray. Yeah. Okay. 240 does the same thing. 240 is right here, but has a negative radius. So it goes through and ends up on the other side. 270 has a R value of -1. So 270 is down here, but we go through the origin, so we end up on this side. Okay, and then we end up with some symmetry that repeats that over here to the left. Okay, so it looks like we have like a little circle within a circle. So I'm going to switch to radian mode so I can see what the calculator shows me. Okay, it kind of loops around. You can watch the calculator as it draws it. There's a little bit of a dip here that we don't see just because we only picked certain theta values. If we picked a few more or picked some between our special angles, we could have ended up with the ones that gave us that little dip. Okay, and it spins around out here, and it dips under through the origin, and then it spins around. It's almost kind of like, I don't know, it reminds me of like a snail or something like that. That's what I think of. Okay, so these have a very strange name. It's a French name. I don't do French, so I'm not very good at saying it. Some people say limacons, some people say limacons. There's probably something weird you have to do with that C with the little swirly on the bottom, but like I said, anybody do French? French? No? Okay. Yeah. So, anyways, these are called limacons. We're going to go with limacons. Okay? The ratio of A over B determines their shape. Okay? A over B determines their shape. So if A over B is less than 1, that's what just happened right here. A is the first constant, B is the constant with the trig function, so 1 over 2, that's less than 1, so that's when we end up with an inner loop. If A over B is equal to 1, that was the first example we looked at with these. It's kind of heart-shaped. They have a specific name, they're called cardioids, because they're heart-shaped. And then if A over B is between 1 and 2, then it's just dimpled. There's just a dent in the side of it, and there's no loop. And then if A over B is greater than 2, there's no dimple and there's no loop. It's like a circle with a flat side to it, almost. Not quite flat, but just kind of flattened out a little bit. It looks kind of like a circle, but kind of flattens out. And then depending on which trig function you've got, if it's sine, it's going to be on the y-axis. Both of these, or no, yeah, see, sine, it was on the y-axis. The first one, cosine, it was on the x-axis. Okay? All right. Almost done. Okay, let's look at this one. 4 sine of 2 theta. Okay, 4 sine of 2 theta. I don't know about you, but I'm tired of filling in the tables. So let's just look at the graph. So 4 sine of 2 theta. Make sure you're in radian and polar mode. And then we can press graph. I'm zoomed too far in. Let me adjust my window. -4. Notice when you go to your window, there's like a lot more stuff than just the X-Men, X-Max and stuff. Don't worry about the first part. Don't touch the first part or it won't graph correctly. Okay, so I just made my window -4 to 4 in all directions. So we know a flower or a butterfly, whichever way you want to look at it. Okay. Let me square it up though. Okay, so these petals are at their maximum. They're 4 units out. So 1, 2, 3, 4, and that comes from the fact that there's the 4 in front. So we've got 4 here, 4 here, 4 here, and 4 here. Okay, and then they kind of loop around. It would look a lot prettier if I had more points, but we're just going to roll with it. Aw, thanks. I know it's not. It's very unsymmetric, and that drives me crazy, but that's okay. It's all good. Okay, so most of you said that it does look like a flower, and we call these rose curves. Okay, they're called rose curves. I know it doesn't really look like a rose, but you know, anyways. So when you have a multiple with the theta, okay, when you have a multiple with the theta, that is going to create a rose curve. So here's the interesting thing. If n is an even number, then the rose has 2 n petals. So here we had 2 theta, so that's an even number. So we ended up with 4 petals. If n is odd, then it has that number of petals. Okay, so this is like what we just did. And notice the A, the constant in front, is the length of your petal at its maximum. Okay, but then if we had cosine of 3 theta, then we would only have 3 petals. And they're always evenly and symmetrically distributed. Okay, they're always evenly and symmetrically distributed. So if it's 4 theta, then you're going to end up with 8 petals. If it's 5 theta, you just have 5 petals. And you could keep going with that. Infinitely many number of petals that can change. Okay, so those are our rose curves. They're kind of fun. I think they're pretty. Okay, let's look at one more. Okay, what if we have r squared? Notice this equation is just like the one we just had, except it's r squared instead of r. So if you're going to plug this into your calculator, then you have to, what would we have to do? Take the square root. Okay, we have to take the square root. And I do believe that we need to include the positive and the negative square root. So you have to type in 2 equations to get the entire graph. Or maybe you're just supposed to put in 1. Hang on that for just a second. I think it just repeats. Yeah, it just traces itself over. You really don't have to worry about 1, but that's okay. All right, so we end up with this kind of infinity-looking thing, or half the flower, however you want to look at it. But notice this time its petal is linked 2 because we took the square root. That kind of makes sense, right? So we come out 2 and 2, and it's a little bit squattier than the other one. so these are called lemniscates. They're called lemniscates. So when it is squared, it's only like half of the rows. Okay, it's only like half the rows. And apparently it's always 2 theta. I don't know why, but it's always 2 theta. So that's the graph that you end up with. The sines are kind of catty-cornered. They don't end up vertical, but the cosine ones do end up horizontal. So it's kind of interesting. Polar is kind of its own little world. It's very different from anything that we've done before. All right, so I know that I just kind of hit the high spots. I am not in any way kind of expecting you to have